AI and thermodynamics, like not exactly two things you'd picture together, are they? One's all algorithms, data, the other's what, like the laws of physics, heat, all that. But that's what's so cool about this deep dive. We're looking at your research, saying we could actually use thermodynamics to make AI way faster.
It's wild how this research brings these two totally different things together.
Right.
It's all about Bayesian inference, this core part of AI that basically lets machines learn from new info and kind of update what they think about the world.
Like giving AI the ability to, learn from experience, right?
Right, yeah.
Yeah.
But the paper mentions this process, Bayesian inference. It can be a real resource hog. Lots of time, tons of energy to crunch those numbers, especially as things get more complex.
And that's the roadblock this research is trying to blast through.
Think of it this way. A room jammed with people, all talking at once, trying to share their thoughts, right? Chaos. Totally inefficient. Now picture a system where those opinions just kind of like naturally blend together, finding a consensus like heat spreading out evenly in a room, effortlessly hitting that equilibrium.
Okay, I see where you're going with this. This is where those thermodynamic circuits come in, using actual physical systems to do these crazy calculations.
Exactly. They're talking about using electronic circuits that basically act like thermodynamic systems to do this Bayesian inference. They even went all in designing these circuits, full-on resistors, inductors, transistors, all perfectly placed to represent the math behind Bayesian inference.
I'm looking at this circuit diagram in the paper now, and I gotta say, bit intimidating, not gonna lie. But before we, really get into it, can you give me the gist? What do these components actually do? How do resistors and capacitors make AI faster?
Think of it like this. We're translating math into the language of physics, right?
Okay.
Take a resistor. It's like a narrow pipe restricting water flow. Higher the resistance, slower the flow. In these circuits, they're controlling the flow of electricity, just like certain variables affect a Bayesian calculation.
So it's a physical version of the math happening. Pretty clever.
Exactly. And they didn't just stop at the design, right? They wanted to make sure these circuits would actually work. That's where spicy simulations come in.
Okay, now that is something I've heard a lot in tech, but to be honest, not sure I totally get it. Break it down.
Picture this. You have this virtual lab, right? You build and test electronic circuits, but without actually, like, soldering anything.
Okay.
That's basically what spicy software does. It lets researchers model how circuits will act in real life, how electricity flows, voltages change, and most importantly, if the whole thing does what it's supposed to do.
A safety net, so to speak. Make sure their design holds up before they build the real deal.
Precisely. And in this case, the simulations, really promising, showed the circuits acted like they should, those components really mimicking the thermodynamics, and crucially, spitting out results that match up with Bayesian inference.
Okay, so they designed these circuits and they've shown that they should work. But what real life AI problems can this be used for?
They focused on two big ones in machine learning. First up, the Gaussian model. Sounds fancy.
It does.
But it's basically a simplified way to show when our starting knowledge and the new data we give the AI both follow that classic bell curve distribution. Super common in lots of AI.
Okay, so nice, predictable data.
Yeah.
But AI often has to deal with like messier, less predictable stuff, right?
You got it. And that's their second example, Bayesian logistic regression. This one's a bit more intense, used for, say, training AI to tell the difference between, like, I don't know, cat pictures and dog pictures.
Sure, yeah.
What makes it trickier is that the data and the outcomes, they might not be linear. Not as easy as saying if this, then that. There's more to it.
So how do these thermodynamic circuits handle that then?
That's where their design really shines. But before we get into it, let's take a step back and understand why this problem, Bayesian logistic regression, why it's such a pain for regular computers, and why this new way of doing things is such a big deal.
Okay, let's do that. A deep dive within a deep dive. I like it. Okay, so back to Bayesian logistic regression, this more complex AI problem. But before we get into how those circuits handle it, tell me, why is this kind of problem so hard in the first place?
It boils down to this thing in Bayesian inference, right? It's called non-Gaussian sampling.
Okay,
So imagine trying to predict a yes or no. Like, will it rain tomorrow?
right.
Regular computers, they're great with data that fits into those bell curves,
Yeah.
like temperatures over a week.
Yeah,
But when those probabilities get messy, don't fit that nice curve, things get tough.
like fitting square pegs in round holes.
Exactly. And with Bayesian logistic regression, you're dealing with these non-Gaussian probabilities a lot. It's like trying to predict rain. in a place where the weather's all over the place. Traditional computers, they struggle to grab samples from these weird probability spreads, which slows everything down.
And that's where these thermodynamic circuits come in. They're better at navigating that probability jungle.
That's the exciting part. The simulations, they hint that this circuit, the one for Bayesian logistic regression, it can handle that non-Gaussian sampling way more efficiently, like finding a shortcut through all the, computational mess.
Okay, that's huge. If they can crack non-Gaussian sampling, it's not just speed, right? It's about opening up a whole new world of AI research, stuff we thought was impossible because it was too computationally expensive.
Absolutely. We could be looking at AI that can handle way more complex, nuanced problems. Stuff like, imagine AI making good predictions in things like medicine or economics, where the data is just naturally all over the place.
So we've gone from making AI faster to maybe even changing what AI can do. Mind-blowing. But back to the how for a sec. How do we even know how well these circuits are doing? It's not like a simple right or wrong answer. It's probabilities, yeah.
You're right. We need special tools to judge how well they're doing. One of the big ones is something called the Wasserstein distance.
Okay, gotta admit, that one sounds a little intimidating. ELI5 version.
Sure, picture two piles of sand, right?
Okay.
You want to know how different they are? But you don't just care about how much sand, you care about the shape of each pile, too.
I'm picturing it. So like a tall, pointy pile versus a wide, flat one.
Yeah.
Those would have a bigger Wasserstein distance.
Exactly. It measures how much work it'd take to make one pile look like the other.
Okay.
In the research, it's used to compare the probabilities the circuit spits out to the, mathematically perfect ones. The closer they are, the better the circuit's performing.
So it's like finding the best way to build a sandcastle, but instead of buckets and shovels, we're using thermodynamics. Way cooler, right?
I like it. But it's not just about getting the right shape.
Right.
We also got to think about how long it takes to build that sandcastle and how much energy we're using.
Right. Because a super fast sandcastle robot that needs a power plant to run isn't very practical. And I'm guessing that's where time complexity and energy complexity come in.
You got it. Super important for figuring out how efficient any computation is, including our thermodynamic circuits. Time complexity is all about how much longer it takes to solve something as the problem gets bigger, like sorting a deck of cards versus a whole library.
Okay, that makes sense. Bigger task, more time. What about energy complexity?
Same idea, but with energy. How much a system needs to solve a problem. Think of a light bulb versus a space heater. Both make heat, but the heater uses way more energy.
So we want these circuits to solve those Bayesian inference problems fast, but without, needing a power plant, right?
Exactly. Efficiency on all fronts. And that's just what the researchers dug into.
All right, let's hear it. What their analysis show? Are we talking small improvements or something groundbreaking? So we're talking about time and energy, the big stuff. What kind of results did they actually get?
This is where it gets really cool, right? Their analysis, those simulations, they suggest these circuits could, completely change the game, blow traditional methods away.
Seriously? That much faster?
It's not even just faster. It's about changing how it all works. Remember that bottleneck we talked about?
Yeah.
Traditional stuff, it hits a wall. Time and energy just go through the roof as the problem grows. But this thermodynamic approach, it might actually break right through that.
Hold on. So they could fundamentally change how we even think about AI computation. That's like a whole different ballgame.
Totally. The research was on those specific examples, right? Gaussian,
Yeah.
Bayesian logistic regression, all that. But the point is, this could apply way beyond that. We're talking about AI capabilities that we thought were decades away because they take so much computing power.
So not just faster AI, but AI that can do things we never thought possible. What was the most mind-blowing part for you?
For me, it's how elegant it is. Connecting something like thermodynamics, this fundamental law of the universe, to AI. It reminds you AI isn't just code on a screen. It's about understanding the very nature of, computation itself.
It's like they built a bridge between two things that seemed totally unrelated. And that bridge could lead to some wild places. But let's be real for a sec. Every big idea has its challenges, right? What needs to happen to bring this tech to life?
You're right. Still early stages. The researchers even say, yeah, the examples look good, but there's a ton of Bayesian problems out there, designing and testing circuits for all those. That's a whole thing.
It's like we've got this awesome engine, now we got to build the car around it.
Exactly. And then they're scaling it up, taking these circuits from the drawing board to handling, real-world AI. That's a massive engineering challenge.
But imagine if they do. Imagine this thermodynamic approach helping us with the biggest AI puzzles. Truly self-driving cars that actually work. AI that can think and learn more like we do.
The potential is
Yeah.
huge if we can actually use physics to power AI. Who knows what we could achieve?
There you have it, everyone. We took a deep dive into an AI future powered by not just algorithms and data, but maybe, just maybe, the fundamental laws of thermodynamics. And from what we've heard, that future's looking bright. And a little bit warmer, I guess.
It's a really exciting time to be working at the crossroads of these fields, that's for sure.
Yeah.